also, I was working on completely different things. This is the first thing. And second thing is because some of these projects, which I will talk about here, they have some follow-up, so I work on some of them, I continue to work on some of them, and if you have some ideas how that could be useful for you, or like I would be happy to share or discuss with you. And actually here, so you see one of the teasers. I'm not sure that we will get that far to that, because this is a map of Belgium with the data which we displayed here using this HCTRW application for delays of trains. How basically train delays are traveling in a network. And this is some of the application which is really I'm excited about, because first of all this has to do with transport. This is the first topic which I'm very interested in. And the second one is, has to do something with networks, how something travels over network. And the piece of work which I will present here, it's partially something which I was doing as part of my postdoc in Tupikina in Porous laboratory. It's this French-Russian center in Moscow, which you all are very welcome to visit. Also Moscow Institute of Physics and Technology and CREEP. So it's basically part of work which I have done with different laboratories, and that's why I have it here. So my background, essentially, it's mathematics. I was working on morphisms of matrices. That was a long time ago in Moscow. Then afterwards, I switched more towards data applications. So we were working actually on data analysis, how you can represent some big data which can come from stochastic, very noisy time series, and you can represent them as networks. And sometimes it was efficient, sometimes it was not efficient at all. So then afterwards, I was working more on biology applications. It was actually more stochastic processes in cells, browsing behavior in cells, so anomalous diffusion. And then afterwards, I switched more towards kind of transport, but what different types of transport, more on large scale, like in global, in the transportation networks. So that's the background. So this talk will be essentially about two things. Since you all are, as far as I know, most of you have a really strong mathematical background, so we will talk first about random walks theory and some of the applications and advances of heterogeneous random walks. This will be the first part. And then, if we will have enough time, and if we will talk also about some applications of heterogeneous or real-world examples. While real-world in brackets, because they are not really real-world, right? It's our representations. So how it all started for us was that basically the story was the following, that I was attending this Molkovsky Congress. It's this big congress, maybe some of you know who work on random walks, this big congress dedicated to Molkovsky, who was working a lot on diffusion topics. It's a congress which happens in Poland, and there all these people who work on random walks theory, who not just introduce some of the continuous time random walks model generalizations, for example, some generalizations of famous Montreal-Weiss equations and so on. So these big guys came there, and I was giving a talk there, and I presented some model, and they were like asking the questions, okay, if you present some model, right, for example, if you present the model of continuous time random walk, and you present also closed form mathematical solutions for this model, what can it be useful for? Like, okay, you can present a mathematical model, but what is the main really drive? Why do you work on that? And my answer for that was the following, that actually, since I was from a mathematical background, and I was never working with data, but I was working in the group of condensed matter physicists. And condensed matter physics, it's very interesting to work there because they have a lot of difficult phenomena they work with, and one of them was actually work to understand how water diffuses in porous media. So, as you know, this process has been studied a lot. Like, people were in Shell, for example, they were very interested in this because there is this application of how oil diffuses, right, through the soil. So there have been a lot of interest. But the problem in these models, existing models, that they are intrinsically, well, intrinsically we'll talk about it, but they're intrinsically homogeneous. So you all know, right, continuous time random walk model, at least random walk model, that I'm basically blind. I don't know where I can go. I can go step forward, step backward with some probability fixed. to the right, to the left, for example, or if in higher dimensions, I can walk somewhere with some certain probability. And usually the main question is, what is the probability that at some point in time, I will find myself in some point in space, right? So if you know the solution, you may estimate how efficient your process is and so on. But usually the closed-form solutions for these models, they assume some kind of homogeneity, because we will talk this about. Because of this formula, so the advances of the models which have been studying this kind of transport of the random walk, which is homogeneous in time or in space, that it diffuses, they rely on the assumption that your, for example, process, right? So if we consider, for example, the process of the random walk, which basically is diffusing, for example, along one line, right? It jumps, but it can also wait, for example, sometimes. So the model of continuous time random walk, for example, is the following: that it's no longer kind of homogeneous in time, because I am jumping somewhere and I can wait with some certain probability, which is driven from a certain distribution. And this distribution in this case is called psi from t. It is fixed, right? It's fixed. And so the closed-form solution, which Montreal and Weiss came out with, and I invite you to study this paper if you want more details, they find the solution in the Laplace domain, right? Which basically tells you what physicists call propagator, or the probability distribution of finding the random walk in a certain amount of time and space. And so what our basically question was, what is the main question from these models is usually, okay, if you know the probability that you will find some particle in some point in time and space, how can you estimate that some particle will actually reach somewhere for the first time, right? It's first passage time probability. And apparently there have been a lot of problems with estimation of first passage time probabilities and distributions. I don't know how many of you have worked, I mean, just so that maybe I repeat, and this is very old known things for you, no? Okay, then I will allow myself to introduce this, because there is this very famous book by Sidney Redner from Santa Fe Institute, which I totally like a lot in this topic. And it's a guide to first passage time. So basically, the guy who basically walks around until he reaches the cliff. And the moment when he first time reaches the cliff, it's a moment of first passage time. And there is this very famous technique, right, which using this the equation which you see here to derive the probability of to arrive at some point of time. Using the distribution, assuming that we know the first passage time, we can derive the probability. But to estimate the first passage time from the probability itself, right? Sometimes it's a challenging problem. I mean, mathematically, right? So basically, you need to invert this, and to estimate it, it's not so easy. And it turns out also that in physical models, if you want to understand how efficiently, for example, the water diffuses from one point to another, it's actually useful thing to know if you want to understand that. And so the challenges here, which we also face here, is also that if we have on top of all this process, right, of the random walk, which is homogeneous, that it's also heterogeneous. For example, that the random walk needs to diffuse some heterogeneous media to estimate the first passage time for such random walk, for which you also don't know the probability of the propagator, it becomes even more challenging problem. So what physicists do when they deal with these problems, they simplify these things, right? So that's also something which we also tried to do here, and this is one of like 5 slides we will spend now on defining some simplified model for which I claim we partially can solve this problem of estimation of first passage time, of estimation of a propagator, and further applications to that for some, well, also simplified structures. So what's exactly what we will simplify here? First of all, we will say that our dynamics, for example, in porous media or dynamics in some media, we will present it as the natural, right? So we will deal with some random walk, which works on a network, and which can stay in some nodes for some time. But here, not as in the model of continuous time random walk of HCTRW, which you all know, we will assume the time which random walk spends in each of these links, it will not be obeying the same distribution. And we will see how much this actually changes the whole distributions for the first passage times. So this model which we introduced with a colleague and then afterwards we developed it further with other colleagues is so-called HCTRW because it's heterogeneous continuous time random walk model. And it essentially relies on two ingredients. The first one it's transition matrix. So basically it's a Markov matrix, Markovian metric. A transition metric which is stochastic matrix. And the second ingredient, it's heterogeneous travel time distributions. So basically, you can consider this model as a model where you have each link, which has some travel time distribution. So basically, you say you know more or less how much time it will take you to go from the node X to X prime, right? So you actually know not just the time it takes, but the distribution which it is driven from. And from this, we define the so-called generalized transition matrix. Why do we care about this and why it's interesting? I will tell you in a second. Because actually it allows to generalize the continuous time random walk solution for the propagator. So if we will remember, maybe you remember the formula which I showed you before, the known solution from the continuous time random walk model, which also tells you about the probability P from X to find the random walk at time t, but here we describe it in the Laplace domain. So we describe it in time. Right, basically we do the Laplace transform of the px from t, which becomes s. And then the closed form solution looks like this, where who x from s is this heterogeneous matrix, where we can basically insert all the heterogeneities from our environment. It may look a bit more difficult to understand, but we will see the plots now, and we will see how useful it can show us basically which are the heterogeneities. But you remember, this is the first challenge of our topic, how to deal with heterogeneities, which are all now in our matrix QS, right? So all the heterogeneities, they can enter here, and in the paper we describe how we derive it. But the second thing is also that we also can derive this long time asymptotic behavior from this, using the assumption that we also have some of the known eigenvectors and eigenvalues, which are very difficult to estimate for general matrices. So if you will take any matrix, you will ask me, how do we actually get to the eigenvectors? I will answer that I don't know actually, but for some good matrices, underlying matrices, right, the eigenvalues or eigenvectors we can estimate, and we know it thanks to the specialists on the graph theory. So, yeah, if you have any questions, please interrupt me because I don't want to lose you. So the results here, the main results basically were the following: that we first wanted to apply this model and to consider on the simple model, also the simplest possible graph, which is the line, right? What the mathematicians always start with. So in the line, what we did is the following: we basically introduced the heterogeneous node, one heterogeneous node where random walk is stuck, right? So in all other nodes, random walk can diffuse as it wants, as it goes in HCTRW. So in the homogeneous continuous time random walk. And basically just because of one node, which is heterogeneous, where you have the polar behavior of waiting times, just because of one node, what you call the tails in physics, right? The tails of first passage time distributions change. Just because of one node. Assume if you put actually many heterogeneous nodes, the tails actually can change. This is something which we calculate for the first passage time distributions. How one can read these plots, right? I mean, like when I looked at them, I first didn't really see it, but then physicists were very happy about them Because when you actually see that some kind of heterogeneity, which is intrinsically introduced in your model, can change asymptotic behavior, it actually is interesting, right? And then afterwards, of course, you want to see that for some kind of more complex structures, right? So if you already see that the change of the behavior can be seen for saline, how it can be seen for example, more difficult graphs. For example, if we take the graph which is more complex, for example, like London Metro, and we know that if we put a random walk on a line of London Metro, and it will basically, depending on where it starts, right, you will also assume, that you will have different first passage time distribution. So first passage time distribution is something which we also look at as our kind of diagnosis for our network, because first passage time tells you how fast or how efficient your transport in your network is. And what it tells you also, it kind of zooms into dynamics on a network. And here we see actually that depending on where, I tell you this because I didn't write it in the plot, sorry, that basically depending on from where the random walk starts, the curve of the first passage time, right? So this, the curve of the first passage time, it usually has a peak. Do you know what in first passage time the peak of the curve corresponds to? Like basically to the most probable first passage time. So basically I have my home, like around Park Montsouris, and I come here. The most probable first passage time to come to Links, like for example around 15 minutes, that will be here. But sometimes there is traffic jam, so the times first passage time can be a bit more. Sometimes I'm very fast and I can reach here less, but in general, first passage time curve, it will be kind of with one peak. And for some networks, especially for some heterogeneous networks, curves can look very, very particular way. And our message was to test it for networks because apparently it hasn't been really tested so far before. So that was for London. But what about some other generic networks, right? Because if you're a mathematician, you may ask, okay, well, you did it for line and for London, but what about other networks? So the way how we compute this quantity of passage time is the following: is that if you are in the Laplace domain, this property, the density of the first passage time in Laplace domain is computed as a proportion between the propagator px0 xa, where xa is your absorbing node. And then you need to inverse it, and it's a very computationally expensive, actually, numerical procedure. You need to apply some techniques to speeding up, but we deal with very small networks. But what I want to stress here is that for a given network, we always expect to have a peak, only one peak, which will be corresponding to the random walk to reach, right, some place in the most efficient way. And we may also have a tail which will depend on what? On the heterogeneous, on the time delay, basically how much you are stuck in some node in your network, in your node. So and in first passage time community, actually, because it's a lot of people working on that, for them it was kind of interesting correspondence to the results which also have been found for some very difficult forms of continuous domains, right? Because here we are in discrete comics. So for some of the models which we were generating for networks, which were kind of different types of structures, for example, when you take more tree-like networks, and those networks which are less tree-like, they're not trees anymore, you also expect to have different characteristics of first passage time, right? Why do you have this is also because of several reasons. Because of, first of all, random walk when it explores your network, and when you also, sometimes it is stuck in one node, which we are calling heterogeneous, it reacts on it also differently, right? And in the network which is not so much the tree-like, the heterogeneity
will be less kind of strongly observed. And that's why most of the plots here, I mean, most of the first passage time distributions in non-tree-like networks, they will still look the same on a long term, right? Because random walk will basically, on the long term, will forget about heterogeneity. It will find its way. But in a tree-like network, right, you expect that if a random walk is stuck somewhere, it will wait, it will need to wait there. So it will really strongly depend on a structure, where it is. So yeah, I think that I should really a bit move further, but just here I wanted to stress that the main, one of the motivation for this model to be introduced was to study the simplified version of heterogeneous continuous dynamics. And one of the kind of my naive application which I thought about was actually transportation network. Because in transportation network I thought first that it was following very similar idea that basically if you are, for example, willing to come somewhere, you may find some of the roads which have some occupancy, right? So you have in a city a road occupancy which changes over time and during the day. And if you want to come to some place, if you know from the data the road occupancy, you may estimate how likely you are to get somewhere, right? So the first passage time basically. But very quickly I understood that first of all the occupancy changes also over time, and also the real underlying network, even if you manage to model it, when you travel you are not random walk. So what you will measure actually, it will not be efficiency of your transport, but maybe efficiency for some epidemics spreading in a network. So, but it will not really be transportational quantities. That was a second kind of critics to this application. So that's why I worked actually on some continuous linear derivations from this model, because as you know, some fractional diffusion equations which you derive, for example, for studying anomalous diffusion in cells, right? The Liubov derivatives, like fractional derivatives, they can be derived from this type of continuous time random walks. So that was actually second application of that. But let me go back now to more like the application to the mobility studies, because there is one of the known application which has been already, I think, around for like maybe 10 years. So this, maybe you can guess what it is, actually. So it's mobility, but of what? So it was a famous paper by Brockman and his group, they were trying to study mobility. But even before GDPR, right, you had many issues with privacy. So that's why people couldn't study mobility of people, they could study mobility of banknotes, right? And so banknotes, they kind of follow the same patterns. For example, if I pay here and I pay in Strasbourg, so it means that this banknote traveled from here to there. And so they had a big database of human kind of traces. Of course, they were not following all the human traces, but still they were following some of them. And they were basically, they assumed that all of those traces, they could be represented and plotted as a distributions for kind of random walk behavior. We'll assume that we have at the same time some distribution of jumps, and this is actually something which is shown here. It's a proportion of number of jumps with a certain length, and they also follow quite interesting kind of almost like a, well, I don't like to say Paolo because everything looks like Paolo on a local plot, but they were quite happy to find it. So, and that was actually one of the reasons why Brockman and his classers suggested actually continuous time random walk model as the kind of underlying dynamical model for human behavior. Why I'm saying kind of? Because here we do not assume, we assume here that all people are homogeneously traveling. So we don't say that all people are different, right? Because I obviously travel differently than Lorenzo because Lorenzo has his own patterns of traveling. But at the same time, what they found was an interesting observation about mean square displacement. And mean square displacement is another quantity which also usually quantum metaphysicists were teaching to look at, because if you look at how much in time so the square, the mean squared delta x basically of your travel is scaling with time. If you get that it scales with time linearly, then you get kind of normal behavior. If it scales a bit with alpha, which is less than 1, it will give you kind of sub-diffusive behavior, right? And this was also something which was observed also partially in the data, and I invite you also to look at these interesting papers who were telling more insights on that. And actually, here in Bell Labs, there is one application on which I started to work on, the movement Saclay, with the colleagues here, where basically if you actually record your trajectory, you can actually analyze it. And if you are more like looking to analysis of your trajectory, you can also look at your data from Google, if Google allows you to give the data. I mean, now it does, but and interestingly, actually, if you plot your own distributions of displacements, if you wait long enough, it will follow some similar laws. But sometimes, and this is also because we change mode of transport, it will not actually obey the same laws. So that's why I wrote here that the scaling of jump lengths for single mode, so if I only check my walks, right, will be like log normal. But if I will check all transport nodes, it will follow more like broken power law. So this was actually second application to which I'm still going on. And if you are also interested to look into more like the data for log time, Microsoft collected also this very interesting open data for geo-trajectory, geo-life. It's open to analyze also for everyone. If you are searching for it for your applications, you are more than welcome to look at it. Basically here the nice thing was that it was very long trajectory, and it was collected in different cities, which was also very surprising to me because nowadays it's very difficult to find such kind of patterns and I mean such kind of open trajectories. Here actually, so this was another part of application, but when I say application, I don't exactly mean that heterogeneous continuous time random walk first passage time distribution was very easy to estimate here for several reasons, which I can discuss. But we can look first at the left pattern here. So what we see here is the delay. So there are basically trains in Belgium. They have very interesting patterns that actually almost every train is late, basically there. And also since they had open data, we scrapped it and we started to analyze it, how basically delays are traveling with time in the network. And you may also wonder then how much time it will take the train delay to travel from Brussels to some other Namur, for example. So that's why if you basically know underlying matrix Q, and you know more or less on average patterns of psi x, x prime t, you basically then just need to apply the formula to look at that. That's one of the ongoing work which I'm working with the Utrecht Complexity Center, where they basically have the connections with actually transportational companies, where for them it's very actually interesting to look at how fast delays are traveling, because there are a lot of problems also how tracks are arranged. So it's not really as simple, because here we assume that graphs don't have, for example, multiple links. They cannot be encoded in matrix Q. So we need to kind of set up a different model for that. And here also, when I was working on open data for bikes networks, we also the problem was that bikes trips. They also heterogeneously distributed. Sometimes you have a lot of bikes in one area, sometimes you have not so many bike stations in the area. And the idea here was that, okay, if you are given just nodes and you don't have links, but you have links which represent basically trips, can you find optimal graph or like the graph of the most popular trips so that you could see the structure of your graph? So it's basically inverse kind of problem in this case. And here, since actually some people here are like Marco and Fabien, here I wanted to also say that one of the projects which we're working with Mark, who will be actually here next week, because with him we're working on the knowledge mapping, but knowledge in the sense of archive. So we are working on this project now where we scrap basically some of the data of how people are publishing in different resources, and if you have published in one place and then you published also in another, how basically this how this kind of trajectory will evolve from one author to another. So basically, for example, this is my trajectory because I published in one place and another, and then afterwards you can wonder whether this will be an epic flight or whether it will be more like a random walk, right? Because you can consider this in different ways. But Mark will talk maybe more about this. Also, there is another very nice project which I will invite you to look at. It's called VLearn. It was developed at CRE, and it's a very nice browser application for actually also navigation in virtual space. So basically what they have done also, they were trying to map how people are browsing Wikipedia pages. So I, for example, browse because I always forget some, I don't know, long, short, term, memory networks, and then I browse this. So basically then my map, my knowledge map, can be projected, like using Disney or any type of projection, as my knowledge map. And then afterwards I can say that, okay, if I visited some of the pages, and these pages in Wikipedia metrics, maybe the one which you are now introducing, if these pages are very, very close by their, by somehow the metrics which you introduced, how can I, as a user of Wikipedia, how I can represent my trajectory? Is it more like heavy flight, or is it more like that I am always observing something which is close to my topic? How basically I can actually navigate through Wikipedia? This is also something which nicely also can be visualized. Maybe some of the metrics which you're introducing now, it could be very useful for them because, yeah, it's an ongoing project for them. And another epidemics application which I was very excited to work on, but I need to work on that basically during the weekends because it's not directly related to the topic of my main focus now. It's epidemiology application where we were working with colleagues from Indra in Tokyo, where basically we had a map of France and how cows were traveling, right, between different farms. And the nice thing here was that basically in epidemics, right, the problem is not to estimate the probability also of the fact that some epidemics will reach some city, but it's again the time when the first time some process, for example, in this case, right, the epidemic spreading process will reach some city. And so here, with a student of ours, we estimated these basic distributions of how fast or how often cows are traveling or transported in different places from one node to another. And from this, again, applying this HCTRW approach, we can actually estimate the first passage time distributions. But this is, again, this is ongoing work for which we try now to apply these techniques. But the only kind of insight which we got now that this is also, again, very noisy data for which very difficult it is to estimate these weights of links. Yeah, these are some results. So the open questions here, I need to wrap up here, would be, again, how to define the heterogeneous network measures so that one would actually maybe design them for a particular case. If you're interested in mobility and estimation of the mobility, what that would be. For example, would it be first passage time distribution, which may look very complex for people, right, to read these plots, or would it be something more helpful, like hopefully more easy to represent? Also, of course, the suitable application for this kind of models would be applications to some data sets where you also already intrinsically have this estimation of waiting times, right? Because when you have them already, then you basically have part of the solution, like we had in London, the case of London. There is also another application which I work with the people interested in anomalous diffusion, which is called the heterogeneous dilemma, which basically tells you or asks what is the most suitable equation, suitable in a sense of this dilemma for the heterogeneous continuous time random walk. So basically, how to write a continuous limit of this model, because you can write limits of these microscopically heterogeneous processes in different ways. And this is also kind of open question for us on which we are working with. So basically, we managed to write the generalized mass equation, but then afterwards, from this, one can write in a very different way fractional diffusion equation. And this is something which, in general, is hard problem. So yeah, take-home message would be that yes, the real-world networks are very much more complex, and that's why, if, for example, one wants to work on them, yeah, if you want to discuss, I'm very open with that. Yeah, we also have actually the network seminar at Korea, which you're all also invited. Like Dalia, for example, she was there, and you're very welcome to come. It's every Thursday, and yeah, tomorrow there will be some epidemiologists there talking about that. And yeah, if you're interested, there is also the code for all this work available also on the GitHub, and check out the applications. And thank you very much for that.
Starting point is you consider random walk in the network, and then you take the first passage from one point to another point, but it's no longer, of course, a random walk, but you want to take this first passage distribution as a typical time to reach a point when the walker is not random. For example, with the bike is
yeah, that's why,
random, so
exactly.
How you can justify it?
Yeah, that's why actually I said that would be more a model for epidemic spreading, because in the case of, for example, epidemics, so there are actually two answers to your question. The first one, that the matrix Q can be directed one. So it can be that you say that, okay, if I actually travel somewhere, I can direct my random walk, and I can induce here in this equation Q, and that's what I was actually doing in the case of diffusion in the city, for example, in London, that I was actually directing it, so basically giving it kind of advective term. In a sense, then I was kind of tricking it, because it was no longer a diffusive kind of motion anymore. But second answer is that actually indeed in the city you are not moving as a random walk, but you can actually assume that epidemics, propagation, it can be presented in a way that, okay, it can spread randomly from one person to another, and that's why it can be more useful for the applications of not mobility but more like epidemics mobility. Because like the people from INSERM here, like Tupikina and others, they are more experts, and they were more saying that it would be maybe more the application and not for mobility. Although I really was hoping for that. But yeah.
What I like is the fact there's a possibility to get the structure of the just from the first passage of the random walk statistic, and this reminded me the work of Kostya Alashenkov, Nokia diffusion.
Yes.
He's also looking how you can learn the structure of the graph just via the random walk.
Yeah, yeah. Actually, and Kostya and Denis, they were those people who inspired actually to work on that. And yeah, I mean, Denis Gremenkov, with whom we started this problem, he's working on a copy technique. He was very rigorously willing to understand how that would be possible to find a closed form solution for these kind of problems, and that's something which is generally very hard for continuous domains. So he works a lot on continuous domains dynamics, where these kind of closed form solutions are very hard usually to find. So it was nice that for some networks it's actually possible to do it. Yeah. But yeah.
I got a question on this because I'm sorry I was late, so maybe you mentioned this at the beginning.
No.
But there's a lot of work in the diffusion process in continuous domain, right? Related with the first arrival point and even related to time spent in a given subset of the states.
Yeah.
Share or plenty of people that work hard on that.
Yeah.
So cannot you work the other way around to use these results to find approximations to what you're looking for?
You mean approximations from continuous domains? You
Yes.
mean for that? Yeah, actually that's something which would be interesting because, for example, for porous media, people work on what they call porous networks. I heard about that also from some colleagues, and they basically estimate first porous media as some complex network process, and then afterwards you can, if you know solution in the continuous media, then you can maybe also map this solution to the one which we have in the network. But that's something which would be a dream project. I would be very happy to work on that, but I need just 25 briefs hour in a day. But yeah, it's a beautiful subject, I agree. Yeah.
And what are you doing with moving calculator?
Well, now we just started to discuss with them, but the idea was that some of the measures which we all know, like for example what you were presenting right for the cities, for example, some of the mathematical methods for analysis of that transport on graphs, they could be used for understanding how people are traveling. And so the idea is to discuss with them how this could be used for analysis or understanding of human travels. So that's ongoing. Yeah, but we should discuss. Yeah.
Also, most of your methodology when you're working on data is like you get data and then you try to fit it all together. How do you get the insight from which?
Yeah, we actually were trying to go the hard way in a sense, because we were trying to first have a model and then afterwards to say, okay, we have this beautiful graph, maybe we can try it on there and then see if there is any interesting phenomenon which we actually see on this. So yeah, because if you feed the model like what people were doing, like Brockman and others, work which I really like, you need a lot of also data for that, and not always we have it. So yeah, that's why I was more kind of speculating in a way when we were saying that I was trying to work on mobility, because you need a lot of data to estimate all these waiting times. Like, yeah. But yeah, if you know some people who work on that, I would be very interested to